Learning. I'm really proud of you for coming that far, and I hope you've enjoyed the course by now and you will enjoy it from now on as well. So today we're going to talk about some unsupervised learning methods, including principal component analysis, k-means clustering, and lastly, hierarchical clustering. These are three powerful unsupervised learning techniques. So let's just start with principal component analysis. As you can remember, perhaps, principal component analysis was a way to pre-screen your data. So you want to pre-screen your data such that you find the most variable direction, the direction of your data set that describes most of the variability. That's your first principal component. And the second direction, which is orthogonal to the first one, that describes the rest of the variability, will be the most of the variability which is remained a second principal component, and the third principal component will be orthogonal to both first and second principal component, and it will capture most of the variability that is left, and so on and so forth. The data set we're going to use today is US arrest. That is part of standard R data sets. So let's put the first row names of US arrest to it so that to see what variables we have and what observations we have. The observations we have in rows are different names of our states. We have 50 states, and as you can see with this 10 by 5 matrix, we have all the observations for all the states in the United States of America. So in rows we have the names of, we have observations for Alabama, Alaska, and so on and so forth. In columns, what we have are the values for 4 different variables. So the 4 different variables we will have were different variables for crime and urban population rate. So let's first find the means of these variables. So if you want to find a mean, you can use function apply, and you use mean to explain you're looking after mean. If you were interested in var, you would put just variance. If you were interested in variance, you would just put var and the standard deviation st and so on and so forth. Here, if you set it to 1, it will give you the mean of rows. But mean of rows are not our interest. What is interesting for us is a row of columns, the mean of columns. And the mean of columns or mean of the variables there. So we apply means to US arrest data on each column. And here are the means. The murder has mean 7.78, assault has 170.7, urban population has this mean, and so on and so forth. What we can see here is huge variability within our data, but let's look at the variance of these variables as well. And it can attest that the variability in our data is so much. So urban population and most of the assault actually has the most variability, then urban population and rape and murder. So one thing is important to remember is when you want to use principal component analysis, one of the most important things you may need to do is to standardize your data. And by standardizing your data, you're setting your mean to 0 and variance to 1. So in order to use principal component analysis, the function that is going to be used is called PRComp. So principal component analysis, PRComp. And the first component you need to introduce is the name of the variable you're interested in. And here, if you want to standardize your data, you just set the scale to t, which is scale true. If you're not interested in scaling things and standardizing, you set it to false. Since we saw such variability here in our data, what we do is setting it to true to capture the variability that is in our data set. To give same weight for different variables. And let's look at the names of our PR out. Their model has so many things. It has standard deviation, rotation, center, scale, and x. We're going to explain some of which, including rotation and x, later. So let's start talking about rotation. Rotation matrix provides the principal component loadings. So each column of our rotation contains the corresponding principal component vector for that variable. So, for example, principal component 1 loading on different variables, murder, assault, urban population, and rape are minus 5.3, minus negative 0.58, negative 0.27, negative 0.54. So as you can see, there's more weight on murder, assault, and rape than urban population. So most of the variability can be seen on our 3 crimes: murder, assault, and rape. The second principal component has 0.41 load on murder, 0.18 on assault, very significant, very large 0.87 load on urban population, negative 0.16 on rape. So as we can see, the second most variable direction is mostly on urban area. And here are the rest of the principal components we have, which are usually not too important, because we can easily grasp 2-dimensional scatter plots. If we go above 3 dimensions, we cannot comprehend it anymore. So let's look at the biplot of our principal component now, and by scale 0, meaning it will be scattered around 0. So what we see here are principal component directions. And as we can see, the first principal component we see here are in the direction of our crimes, and the second one is an urban population, as we can see. So as you probably have noticed, that this figure is exactly opposite to what we had earlier. So it's 180 degrees image of, it's actually more than that. It's 270 degrees image, or better say mirror image, of what we had in our textbook. And that is quite natural, because in principal component now you find the direction. In mathematics, it doesn't matter if you find the direction or exactly the opposite of that. Both of them conveys the most variability. So if you want to change everything to positive numbers, it's pretty easy using x component of PR out, the x component of that. And that's exactly what we're going to do now. So we are going to replace rotations with negative numbers of that. That will be the direction, which is 180 degrees to our original direction in 2-dimensional shape. And we do the same thing for x's. X's are our principal component score vectors. So we fix that too. So we fix both x and rotation to minus or negative of the values we had. So let's biplot the new version of it. So let me first run these two. And now let's look at the new cases we have. And as you can see, it's more, it's exactly identical to the graph that we had in our textbook. So it doesn't matter if you have the directions or the directions that are exactly in the opposite way, because if variability is some direction, it's exactly on the opposite way of that as well. So if this is the direction of variability, you can show it with this vector or that vector. Okay. Another thing that is important for us is to see how much of the variability of data can be shown in with our first principal component, second principal component, and so on and so forth. The way you have access to that is through standard deviation vector. So PR var, which is the principal component variances, is standard deviation of what we found squared. And as we all know, variance is just standard deviation squared. So let's run that and let's look at PR var. So as you can see, you see on a scale variances that are being captured with each of these directions. So the first directions show 2.48 of actually the first principal component direction shows 2.48, captures 2.48 or shows 2.48 of the variability. The next one is 0.98 and so on and so forth. As you can see, they do not add up to 1. If you want to scale them and see what is the proportion of the variable that has been captured with each of these principal components, and by the way, this should always be in decreasing order, because the first principal component captures the most of the variability, the second component captures the second most variability, and so on and so forth. So if we want to scale this thing, we need to add these values up and divide each of these components by the summation of all adds. So that's exactly what we do here. We element by element, we divide the values of this variability with the summation of all of these variables. And let's look at PVE now. And the PVE will be relative variability that's been captured by each of these directions. Here, the first principal component captures around 62% of the variability existed in our data, and the second one, 24%. That's a very large value for the first two principal components, and that means only 12 to 13% of the variability was left to the third component and fourth component. So the first two principal components capture almost all of the variability. So we learned how to find principal component vectors and values and scores. We understood how to deal with variances and see how much of the variance has been captured by each of these principal components. And that is all of the things we wanted to discuss about principal components. Now we have these principal component vectors. We can use, let's say, the first two principal components in our regression lines. Now let's move on to the next unsupervised learning method that we have, which is k-means clustering. K-means clustering is a very famous categorizing algorithm, and it assumes that you want to cluster your whole observations into k clusters, and that k stands for that. So let's generate some simulated data. In order to do that, you have to set your seed to a random number, and let's generate 50 by 2 variables, 50 by 2 matrix from a standardized normal distribution. So let's look at X now. So X will look like this. It's 50 observations in 2 variables. All of them are just, all of these values just came from standardized normal distribution, which has mean 0 and a standard deviation 1. If you want to have a very significant or very clear-cut categories, what we need to do is to change some of these variables, some of these values, and just some of these values to new values so that they become completely separable from the values that we have in these 50 observations. And the way we do it is that we first manipulate the first column of the first 25 observations, and the second thing we do is we manipulate the second column or second variable of the first 25 observations. So what we do is we just add 3 to the first variable of our first 25 observations, and we subtract 4 from every observation under second value or second variable. So let's do that. And now let's look at X. So let's plot our adjusted X. So as you can see, 25 observations are roughly here, 25 observations are roughly here, because we just added 3 to our X1 and subtracted 4 from our second group, and so that is why we generated this group. Before this generation, all of the variables would have been here. All of our 15 observations would be in this proxy. Now, since we added 3 to X1 and subtracted 4 from X2, that we generated this second group for these 25 observations. So we are done with generating our data set, the data set we want to work on. In order to use k-means algorithm, the function we want to use is called k-means, so no rocket science. I think it's very hard to forget that function name. It's called k-means. And the values it needs is the data set. Our data set is X. K, you have to introduce K to it. Is it 2, 3, or 4? So let's fix K, the number of clusters we wanted to search upon, to 2. And then you have to introduce nstart. Nstart says how many times should the algorithm start from fresh initial seeds for our category called means. And as you saw, depending on where our initial setting is set, we may end up with different clusters. So we may end up with local minima. So by setting this n-start high, what you will do is simply making your function to search on more random settings so that the probability you end up with the best model will increase. So ideally you want to have this n-start as much as possible. You will want this algorithm to be done over and over and over again so that you make sure you get into the global optimal. So let me run that. And let me look at the names of my k-out. There are several things that are being discussed. The one is clusters. That's an important one. It gives you the labels of the variables that are being clustered in each of the categories. So let's look at the output on cluster. So as you can see, we know that the first 25 observations belong to one category. The second 25 observations belong to the next category. And as we can see here with k equal to 2, our k-means algorithm did a pretty good job, pretty darn good job. So now let's look at the plot of that. So let's plot x based on the colors of these clusters. And here what we do is that we set color to the label of clusters plus 1. So label of these 25 observations is 2. So 2 plus 1 is 3. So color code 3 will be assigned to first 25 observations. And for the second so for the last 25 observations, we assign color label 2 because that is 1 plus 1, which is 2. And here we just want to add a title, and if we want to add a title for it, we just use main. So let's plot that. And as we can see, we see this beautiful clear-cut clustering. So we knew we had 2 clusters. That is something we knew a priori. So that is one of the problems of using k clustering method. Using k, we can change this k to any number that we want, and it will give me different clusters. Choosing the correct k is debatable. The methods that end up with correct k choice is debatable still. I think there is no one method that is accepted by all statisticians. So it suffers from that unless you're absolutely sure there are specific type of categories that you want to talk about. Choosing k is important. So let's play with k and see how things will look like when we change k. So let's use k equal to 4. So the only thing I'm going to change is I set k equal to 4. So let's look at our k-means algorithm output based on 4 categories. So the first category divided into 2 categories. The second category almost, I think these 2 belong to this category before, but now it belongs to this category. But as you can see, if you change k, you're increasing the number of clusters that you have. One of the things we are interested to have access to is within cluster sum of the squares to have an idea of how much error we have in our data set based on our clustering method. And the way you can get access to that is by calling tot is started with total, dot within ss. So it's within cluster sum of the squares, or total within cluster sum of the squares error. And as you can see, for k equal to 4, because we just set it to 4, this within cluster is 69.75. So if you want to see how by using different initial points we end up with different clustering methods with different errors, the way you can test it is through using this tot within ss. So we're done with k-means, and here is our last algorithm to tackle, and that is hierarchical clustering. And if you remember, hierarchical clustering starts from finding the 2 closest observations, put them in one cluster, and then use that as one entity and tries to find the next cluster, and does it until the time you only have one cluster. So you see all clusters simultaneously. One of the problems we dealt with was the way we we consider the distance of one cluster to observations, one cluster to other clusters. As we saw, there were 4 ways to deal with these linkage distances, and they were complete, average, and single. They were the 3 most one, and as we will see later, one of them is not too impressive, so we always, in most of the application, we stick to 2 of these linkage methods. The function you're going to use is called hclust, so it stands for hierarchical clustering. One thing to remember is, for this, you're not, in contrast to the earlier methods that we just put observations here as one of the elements of inputs, what you need to put here is a notion of distance. Because not only the method you're going to use is important, but also the way you're going to measure distance. You can use distance measure, you can use correlation measure, you can use Euclidean distance, or any other types of distance with different norms. So here we're just using Euclidean distance method, and that's why we put distance of x. X is our observation that we want to cluster upon. So let's use our first hierarchical clustering using linkage method complete. And let's do that for second one as average and last one as single. So let's see these 3 clusters side by side. So the first one, so in order to do that, you have to divide your display into 3 identical subscreens, and the way you do that is using par mf row C1 to 3. That means it has 1 row and 3 columns. So if you wanted to divide it this way, you would write 3 and 1, C3 and 1. So let's plot HC complete. That is based on our complete linkage method. Let's do it for average linkage and single linkage. So in this case, remember we played God. So we intentionally simulate our data so that we have 2 distinctive groups. So as you can see, if we cut our 3 from here, the complete algorithm, the linkage complete algorithm, gives us 2 clusters. And as you look over the labels of the observations that are assigned to each cluster, you will see the first 25 observations, if you cut it from here, the first 25 observations, except 33, is assigned to one of our clusters. And for the second case, all observations that are labeled in second group are correctly labeled. So the only error we see, and remember we played God, so that's the only way we know how we did, was misclassification of 3. We had 2 relatively same size groups if we just cut it from here, and everything seems fine. If we cut it from here, we end up with 4 groups. And I assume the outcomes you get will be very close to the outcomes you got in K-mean 4. So using complete linkage did a very good job. Average linkage does a relatively good job, specifically if you just cut it from here. What you will see is that, again, we have a clear cut that separates my data into 2 different categories. The first 25 observations are correctly identified in one of the categories, and the last 25 observations, or second 25 observations, assigned to the next category. So he did pretty darn good job in assigning things, with the exception of 44 and 46, which was assigned to the group that is here. And I don't see any other problem with this assignment. So it also did a pretty good job in assigning. But as you can see, this 16 is bothersome, specifically if you want to have 3 groups. 16 will become 1 group. Well, when we look at linkage method single, things are getting very ugly. If you want to have 2 categories, you will have 16 and the rest. If we want to have 3 categories, we have 16, 14, and the rest. As you can see, we have so heterogeneous groups. That is why in most of the applications, stick to linkage method of complete on average. I would say stick to complete. Okay, so now let's say you're interested to cut your trees such that it give you four distinctive categories. The way you do that is by using a function called cut_tree. Cut_tree uses the model that you have. Here we have HC complete, and the second element of which is number of clusters you're interested in. So let's cut it for all of these 3 methods, and as you can see, if we just categorize it into 4, so let me start with 2. That might be better. Okay, so let me 2. So as you can see in complete method, when I cut it into 2, with the exception of this observation, everything was fine. In average linkage method, this one was miscategorized, and this one was also miscategorized. In single linkage method, we see that 2 categories are so heterogeneous. One category contained 49 observations, and one category only contained 1 observation. And that's the trouble of that. So if you want to have more categories, you just need to change this number. So here, there is another trick to use. If you in our simulated data, we were extremely prudent to extract our observations from standardized normal distribution. So the variance within group variances are identical for both groups. But sometimes we have different units for x's. And in those cases, it's better to standardize the data and then use it in the in your hierarchical clustering method or functions. The way you scale your data or standardize data is using a function called scale. So let's define a new value or new variable called or new data points called XSC, x scaled, which is scale of x, and then let's redo our algorithms just by getting distance or using this new scale observation. And now let's look at the results. Again, the result we see since from the beginning, our observations were standardized. They had same standard deviation, same standard deviation 1. We don't see too much of a difference in this case by this simulated data. But if you had a data like the crime data we had earlier, the ones that had so much variability from one group to another group, the results you would get from scaling things up would be completely different from the results you get from normal observation. So my suggestion for you is if you want to use hierarchical clustering method, unless units are important for you, there is some underlying assumption under these units and you want your categories be relative to units. I cannot come up with that much of examples that will qualify for that assumption. But if such an assumption exists, refrain from scaling it. But if that assumption doesn't exist, please scale your observations and then use it. Unless your data is already scaled and like the simulated data we had. So today we learned how to deal with principal component analysis. We learned how to use k-means, and lastly, hierarchical clustering. We are done with the R sections of the textbook of amazing textbook of an introduction to statistical learning with application in R, which is written by wonderful people and very esteemed faculty members, James, Witten, Professor Hastie, and Tibshirani. And I am very grateful that they shared this textbook for free online. Everybody can use it, and I'm very grateful that Professor Hastie and Professor Tibshirani gave me the permission to use some of their materials in the class. Thank you so much for your attention. We're done with this textbook, and we hopefully start with new materials from new textbook or new sources. Thank you so much.